Okay, and we're back for the second hour here on Wednesday, July 22nd. Keep in mind these reminders, and especially, we'll be starting 25 next time, and 25 is amines. We'll have a separate chapter on amines, and so test 3 will actually be after we finish chapter 25. So yeah, and that will be our third midterm here toward the end. And then the fourth midterm's right at the end, and then the cumulative final will be coming up. Okay, so we covered the aldol reaction, which is using aldehyde or ketone enolates under hydroxide base conditions or under LDA conditions. We did the controlled aldol also. Now we're going to move forward into the Claisen reaction, which is using esters as electrophiles and nucleophiles. Self-condensation, again, we'll start out with the simple ones here and go through the mechanism. We'll do some crossed Claisen reactions, some intramolecular ones that we'll call the Dieckmann condensation, and see how far we get there. There are some issues here where it's different than the aldol, and now we use the base that corresponds, the alkoxy base that corresponds to the ester. So this is a methyl ester, so we use sodium or potassium methoxide. And the solvent that we use is also corresponding to the ester. We use methanol in this case if this is a methyl ester. A lot of times we'll do the Claisen with ethyl esters, then we'll have to use ethoxide and ethanol. We also quench with dilute acid here to give the final product. So our mechanism will have to account for that. If we just leave it basic here, the actual product will be a salt, okay? And it's different product, of course. We have the beta keto product now, and the carbonyl back being an ester there. So it's a little bit different than the aldol. We have the potential leaving group here within the substrate. So let's go through the mechanism and point out some of the differences and similarities there. Let's go ahead and use methoxide to deprotonate here. Now, methoxide, is a charged nucleophile. Can it be adding here? Yes, it can. That will be a tetrahedral intermediate that will just collapse back and kick off either one here. You can kind of see why you use the base that corresponds to the ester, because if you have a different base than the ester, you can actually get transesterification to occur. And that will give a mixture of products. The reaction, the Claisen, will actually still continue, but this is the productive pathway, okay? So there are equilibrium effects going on. So let's go ahead and form our enolate, which will look like this now. And again, we have the charge up on oxygen. We, of course, have the charge down here also on carbon. It'll look like that with the carbonyl back and that. And again, this is the only reason why you can form a carbanion here. It's because of the resonance stabilization of the carbonyl next door. So it's this alpha position where we can do the deprotonation, right? So either one, you could say, well, this is the nucleophile or that's the nucleophile. Well, this is the nucleophile because we get back the carbonyl resonance. Okay, we talked about that before when we looked at alkylation reactions. So what can occur at this point? We can condense with more of this. So here's our nucleophile that we formed from the deprotonation. Now we're going to add it to the neutral, which is going to be the electrophile. So that part's very similar, of course, to the aldol. So as this comes down, let's go ahead and attack. And what will that look like? O minus, OMe, and there's our ester back on that side. Okay. Now, what's going to occur? Well, here we have a tetrahedral intermediate with a leaving group on it. So this is a different part from the aldol, right? So this can come down, and look, we regenerate the base, the OMe minus, the methoxide alkoxy base. And what does that give us? Oh, look, that gives us the product. That is the product, isn't it? And OMe minus. We should say, oh, we're done with the mechanism now. That's the product. But we're under what? We're under basic conditions here. We haven't added the acid yet, okay? And that's a timing issue, right? This is very fast coming off here. And what else is very fast here? Well, you have a beta keto ester product. So this next step also is very fast of what? Grabbing that proton there and reforming now the much more resonance stable isenolate. In fact, what's the pKa of this? The pKa is 10. It's much more acidic than the starting ester. The starting ester pK is around 20, right? But once it does the Claisen condensation, look, you have the ability to deprotonate this, and this then becomes the actual intermediate in the basic conditions that the product actually adopts there. It's the conjugate base that will sit there like that. And you can draw resonance structures with negative charge here or up onto that oxygen, right, to justify why this pKa is 10 there. In fact, this is the driving force for the reaction. This enolate is more stable than this enolate. And that's why you do the acyl transfer, the Claisen, the tetrahedral, and then loss there. And then the base takes that proton off, and this is the resting state for the product. It sits there until what? You add in the second step, dilute HCl. And why do we say dilute? Well, you just want to go to a pH of 4 or 5. You just want to acidify it slightly. Water will do it too. You know, the pK is 10 there, but yeah, you want to have a little bit more acid strength here. So what do you have? HCl or hydronium ion, right? If you're in water, that will allow you to gently protonate and give the neutral product there. But initially, under the basic conditions, it's this right here, okay? So we've got this issue of, you know, the base, choosing the right base, the right solvent, and then acidifying here. And then that comes out of the mechanism of why we need to do that. Now, if you mix it up, if you have ethoxide or methanol here, you're going to get some ethyl ester, okay, which will be a mixture. The Claisen can still go, but it'll give you a mixture there. And we'll see some other limitations here in a second on the Claisen reaction. So let's look at mixed Claisen first. How about if we take ethyl propanoate and ethyl acetate. Now we have ethyl esters, so we're going to do the Claisen here with sodium ethoxide, and our solvent's going to be ethanol, and we're still going to have to quench with dilute acid. And your challenge now is to figure out how many different products are there. Okay, products, we'll say, how many, okay? Can pause now and figure it out. All right, and we're back. So let's do this one first. We're going to get this product, which will be the ethyl acetate condensing with itself. We're also going to get the propanoate condensing with itself. And that'll look like that. And you should count the carbons there. Make sure you see, you know, 6 total there on the acyl part, not counting the ethyl part, but yeah, the propanoate brings in 3 at a time there. So those are the normal self-condensation Claisen reactions. But this one can do the crossed ones also, right? So what are the cross products? So we can have this one. And that one is what? Where acetate is our nucleophile and the propanoate here is our electrophile, okay? Now that's going to be mixed in there. All 4 of these, I don't have the percentages here, but it's a bad mixture. This is not a good reaction, but it points out, you know, mechanistically what we're keeping track of. And so let's see, we got this one. And that's where the propanoate is the nucleophile and the acetate's the electrophile. So that is different than that one, right? So point out where the carbons are. This must have been the acetate electrophile. There's our strategic bond. That's the bond we just make there, right? So there's a butanoate. So 4 possible constitutional isomers. Are there stereocenters here in any of these? So it's a little simpler than the crossed aldol. I think we had 12 total products there. Here, there's no stereocenters, so it's just 1, 1. How about this one? Oh, we do have a stereocenter there. So that one will be racemic. And then this one too will also be there. We should point out here that a lot of times these will sit as the enol products. So just looking at the acetate ones condensing with each other, the enols will also have a significant amount of percentage there. And I don't have the numbers on that, but remember we saw with the simple one like this, I think it was, this one, what was the percentage of enol there? It was like 70%, 76%, so it's quite high. So these will be quite high too. So are those other constitutional isomers? Yeah, you say they would be. They're tautomers, so you'd have those for each one of these as well. So you can add it up and keep track of that if you'd like there. Let's see. How about where we've got this one? And we'll just look at the self-condensation first of this one. So how about where we have an isopropyl here? So this is what, 2-methyl propanoate. And let's do the reaction there. What would our product look like? Look like this. And have the ethyl ester. And we got to keep track of the carbons. So you have 2 there because it's an isopropyl thing there. I think that's all the carbons, right? Count them up. Yeah, there's 4 coming from each component of the ester there on the acyl part. What's the yield here? Less than 1%. Oh, the others were all in the 70, 80, or even 90%. What's the issue here? Well, there's only 1 alpha hydrogen. What you really need for a high yielding reaction is at least 2 alpha hydrogens. Why? Why is that a requirement? Well, it has to do with that enolate resonance stability after it does the condensation. So let's look at the mechanism here. So yeah, you can form this enolate. That's not the problem. Okay. In fact, that's a more substitute enolate. That'll have higher percentage equilibrium-wise. And you can do the addition here. Even though this is hindered, it's going to be slower than other acyl transfers, but you can get to this intermediate. What's it going to look like? O minus ethoxy, gem dimethyl from the isopropyl. We're looking good, right? All we need to do is kick off ethoxide and go to the product, right? What's a better leaving group, the ethoxide or this more substituted enolate? And plus, let's do it where we do eliminate this and go to the product. Let's see, we'd get this, but we don't have hydrogens here. We have 2 methyls, okay? So what can occur here? Ethoxide actually adds and reverses back. This is reversible because you can't go to the beta keto enolate. Okay? You can't get there from here because there's 2 methyl groups blocking that. So you don't get this resonance stabilization with that beta keto enolate pK of 10. What occurs here in this case is ethoxide's adding here. It's also adding here, but that would be degenerate just going back. But if it adds here in this intermediate, okay, and that looks like, oh, it should be a high yield, right? No, it's less than 1%. So what's really occurring? More ethoxide can go back here, and then what? This can break off here and go back here, which is reversing back to this. This enolate right here is the only stable enolate in the whole system. Why? Because you have this position blocked in the product, okay? So that's a limitation. These only form in trace amounts. You do get a tiny amount of it. If you do it under LDA conditions with the Lewis acid, you can get some of this, but that's with a better leaving group and a better base. I'm not going to talk about those conditions. Under our typical Claisen conditions here, if you don't have at least 2 alpha hydrogens in the nucleophilic part, it's not going to work, okay? So that means what? In the crossed aldol, if you've got some where the electrophile doesn't have the 2 alpha hydrogens, you can do good crossed aldol reactions. So let's see. What can we do here? Let's take one that's going to be this with one that has the alpha hydrogens, sodium ethoxide, and quenched with dilute acid in ethanol. Okay, what's our product going to be here? Well, it's going to be this. And this will be a good yield now. Okay, why is that? Well, here's our nucleophile. Here's our electrophile. Okay, and that's all it can function as. It can't function as the nucleophile. And then once we get that, we've got the full conjugation with our intermediate, which will look like this. So I'm not doing the whole mechanism here. You can see what that mechanism would be after the tetrahedral intermediate and after base takes it off there, because this is a methyl group. It's got 3 alpha hydrogens, right? One is taken off to form the enolate to begin with, but then there's 2 more that can form this very stabilized resonance guy, and then quenching with dilute acid can give us that product. Okay, how about this one? How about if we have this one, plus, let's do, sorry, there's a lot to write here. Dilute acid. Okay, so how's this one going to go? Obviously, it's a crossed Claisen. This one could condense with itself, and that will be a lot of the product. But you see, this one here should only be the electrophile. Why? Well, you can form the enolate there, but if that functions as the enolate, then you'll get to that point where your Claisen adduct, the intermediate's reversible because you don't have that second one to pull off. It's only got 1 alpha hydrogen. So that will reverse back and have this function as what? The electrophile almost exclusively. And most of your products, sorry, I don't have the actual yield there, but you put the one over here that's the electrophile, and then the one over here that's the nucleophile, and you get your product there. Okay, so it's again another crossed aldol there with no self-condensation. Okay, before we do the intramolecular, I want to show you a do-around here. So, and it's using LDA again. LDA is kind of the solution to some of these problems. What if you want this product? Okay, you're not going to do that with a Claisen reaction. What can you do though? You can do this with a Claisen, right? So you can form the beta keto butanoate from a condensation with acetate. And then what can you do? You can deprotonate here with sodium ethoxide and methanol, or methyl iodide rather, okay? That will give you this. And then what can you do? Well, you can take that middle one off, and you don't need LDA in this case. You can just take that off with more sodium ethoxide, right? You've got this second one here, and then it's just a matter of alkylating. Now, alkylation's different, right? With the Claisen, we're talking about, condensing, and you have to get to this type of thing. But this one, right, you can just treat that then with methyl iodide, okay, to get to that product. But again, that's not a direct Claisen approach. It's using the Claisen here, and then alkylating twice, like we learned about with the acetoacetate synthesis. What if you want this type of product? Where you've got, your basic Claisen structure there, but you want to put a group out here. Now, it's easy to alkylate right here. That pK is 10. But what about over here? Well, you can take this type of substrate, which you can get, again, from ethyl acetate Claisen condensation, and then you can treat this with 2 equivalents of LDA. What's going to occur here? Well, the first one that's going to come off is right here, but look, LDA is strong enough to take that one off. The pKa over here is 20, the pKa over here is 10. If you use 2 LDAs, what does this look like? Yeah, it's a dienolate. And it looks kind of funny, but that's okay. You've got the lithium cations in there. you know, separate out these negative charges, whatever. And then what are we going to have to react with? Well, you react it carefully at low temperature with this, which is benzyl bromide, a phenyl with a methylene bromide. You could say benzyl bromide, okay, or represent it like that. It's okay. Which one's going to react first? The one that's pK 10 or the one that was pK 20? Yeah, the more reactive one's out here. And plus, sterically, it's more available. So you're going to get this reaction here, okay? And then what? You carefully quench with dilute acid, and that will just protonate here, and then you can get this type of product. There are ways to put other things at different spots here, but the LDA allows you to do that, and the more reactive spot is the less stable one, the one that came from a higher pKa, 20. But anyway, that's a little bit of a different thing. All right, let's look at intramolecular here, which are going to be Claisen condensations, but with cyclic structures as the products, and they're going to come from diesters. Let's see. Let's take this ester, and I think there's a name here. You can figure out what this should be called. So it's a dimethyl ester. How many carbons? 1, 2, 3, 4, 5, 6. Yeah, what's that name? It's adipate, right? Adipic acid is what it came from originally. Remember, oh my, such good apple pie. Well, there's a part, adipic acid. In fact, ironically, adipic acid is in apples, which helps you keep track of that mnemonic device to remember. But it's the methyl ester of adipic acid, okay? And we're going to treat that with sodium methoxide in methanol then, and then dilute acid at the end. And notice we have two spots. We can form nucleophiles here or here, and it's symmetric, so we don't need to worry about it. Let's just say this is our nucleophile part. We're going to form the enolate there, and then this is going to be our electrophile, okay? So this is a so-called Dieckmann condensation. Don't worry about the name. It'll give the same Claisen type product. You see it's still beta keto ester product, but it forms a ring. So adipate, and we'll see pimelic acid give a 6-member ring, but this 5-member ring strain free. This is a very good way to form 5-member rings. Using this, all these materials are very cheap. This reaction is very efficient that way. So how does it work? Let's go through the mechanism briefly. We've got the anion enolate. You can draw the resonance stabilization there. And then what? We condense that over here with the electrophilic component. We could have used it from either side. It's symmetric. What's our intermediate look like? O minus, OMe on a 5-membered ring. Now count them up. 1, 2, 3, 4, 5. Yeah. And where's the ester? Right there. Okay. And we've got the tetrahedral intermediate again. And bring the electrons back down, kick off the methoxide. And look, there's our product, right? We're done with the mechanism. And you would think so. But no, you're not done with the mechanism. What occurs now? Right, the second hydrogen has to be pulled off. And this is the only reason this works, because it would be freely reversible going back to a more stable enolate here. We didn't have this second one here. So let's use that, OMe. And this is being thorough here on the mechanism. And we could draw the electrons delocalized over here too. Doesn't matter. So I'm just going to one resonance structure here. So we'll have a ketone there. And we'll have the double bond, O minus, OMe. Okay. And methanol, we just create an equivalent of methanol there. And so what's the dilute acid for? It will just reprotonate that. And again, why are we doing that? That's redundant, isn't it? Take the proton off, put it back on. Well, this is under the basic conditions that are needed to do the acyl transfer, okay? We need to drive it to this point here. This is thermodynamically more stable now. This is pKa of 10, again, compared to pKa of 20, that allows us to drive the reaction to this point. and then to get the neutral product and actually isolate it. We can't isolate this during the basic conditions, right? This proton transfer is super fast if you're basic. So it's going to all sit like that. And that's good. That's stabilizing. Okay, so make sure you're comfortable with why we're doing this deprotonation, reprotonation. Okay, and then we bring the electrons back down, and yeah, there's our proton transfer to put that back on there. But if you don't have that second proton to be able to pull off, the Claisen is reversible at that point, and it gives you a very low yield, just trace amounts of that product at the end. So anyway, yeah, keep track of that. So let's do one where we've got a choice here of which side we're going to do the Claisen on. How about this? So here's an adipic acid that has a different substitution pattern, right? So it's methyl ester here and here again, just like before. But look, this ester here has, at the alpha position, a gem dimethyl, 2 methyls group at the 2 position there. Let's do the Claisen. And what do we get here? Well, we've got to make some choices here. How are we going to do this reaction? Where's our nucleophile? Where's our electrophile? Well, the nucleophile can't be here. But can this be our electrophile? Yeah, that's okay. So our nucleophile is going to have to be here, right? So let's go ahead and form it right there. Yeah, verify there's no alpha hydrogens here. So this is a limitation of how you do this Dieckmann condensation. So let's see, we'll get to that intermediate there. And what'll it look like? Have O minus, the dimethyls over there. OMe, you just add, and then the other methyl ester. Sorry, I kind of flipped it around there, didn't I? But there's the bond we just made, right? Adding into that ester. And yeah, it should be a 5-member ring. 1, 2, 3, 4, 5. Yep. And so at this point, we lose methoxide again. And I think you can see the rest of the story there. So we give this product after the end there. So doing the last couple steps. And there are a couple steps, right? We have to reform the enolate there and do that. So you would not use this as the nucleophile, obviously. There's no alpha hydrogen. You can't form the nucleophile over there. So some of these have some limitations, but that's a good yield in that point. All right, let's do the adipate one, where we've got, I'm sorry, the pimelic one. We're going to do that with a couple more, just one more carbon. Yeah. This one will give us a 6-membered ring, I think. 1, 2, 3, 4, 5, 6. Yep, ethyl pimelite. And we'd use sodium ethoxide and ethanol. Again, we could have switched that for methyl. This is just one I saw for the pimelic acid. They used the ethyl ester. And then quench with acid. And what's our product? It's this. 6-membered ring, cyclohexanone with the ester on the side. So those very useful products, right? These cyclic products are formed under high yield from these simple, dicarbonyl diester compounds. Can make all sorts of products there, and we can do different things from that at that point. But yeah, let's see. Let's look at a couple more that involve some other electrophiles. So far we've just been looking at the esters themselves as the electrophiles. You can also condense esters with carbonates and formates. So let's look at some other electrophile components here. So how about if we have something like this? We call that a Chloro Formate. Comes from formic acid. It's the ethyl ester of formic acid, but there's a chloro group here instead of just a hydrogen, which a formate would be. So yeah, we call it chloroformate, and that can function as the electrophile. There's no way that that can be the nucleophile, right? So that's one way to look at it. Or we can have formates themselves. So here's a methyl formate, And so that can accept a nucleophile and then lose that, and that can transfer the aldehyde group. Okay, so that's another useful thing. Or we can use carbonates. Here's ethyl carbonate. And, these will give different products, useful products, and only functioning as the electrophile because they can't be the nucleophile. And this comes from carbonic acid with 2 ethyl groups there. How about this one? How about a formamide? Dimethyl chloroformamide. NN-dimethyl chloroformamide would be the full name for that. And again, some of these we're going to have, choices for what's the leaving group. So on the formates themselves with a hydrogen there, that's not a good leaving group. The methoxy would leave. Chloroformate, we'll get to a tetrahedral intermediate. This will be the better leaving group. Okay, kind of analyze this. Carbonates are both the same. How about the amide one here? Yeah, the chloride will be a good leaving group, not the amide nitrogen. Okay, so let's see a couple of these. How do these work? So you can take cyclohexanone or any ketone or any ester for that matter, and you can form the enolate irreversibly. And so, yeah, the pKa is definitely favoring product, in this case sodium hydride, and that will give us the enolate here. And can actually do that at low temperature, or we can do LDA. LDA will let us, form the kinetic enolate, but this is symmetric at this point, so you can use either one. And then let's see, which one do we want to do? Oh, how about chloro formate? Okay. So let's see here. If we use chloroformate, what's going to be our product? Well, we can analyze this. That's kind of like the Claisen or the aldol. You can say it's back to the aldol. This is the Claisen part, right, where we have an ester for our electrophile. So it's similar to that. It's kind of combining this. This is more of an aldol-like nucleophile. What do we get at that point? We get the ketone back there, and we got our tetrahedral intermediate, which has chloro and ethoxy. Which is the better leaving group? Ethoxy coming off, or chloride? Yeah, chloride's the best leaving group, right? That has the lowest pKa of its conjugate acid, hydrochloric acid -7. pKa of an alcohol, that's 16. So yeah, that's a potential leaving group. And if this was carbonate, where these were both the same ethoxy, then we would kick off an ethoxy group. But here we just kick off the chloride directly. And look, we go right to this. And we can do the same thing with the base conditions. But we use this irreversible strong base at that point. So we don't need to worry about the alkoxy base. We could have used sodium ethoxide. And if we use sodium ethoxide as the base, then we would need to protonate, because the ethoxide then would deprotonate this, okay? So you can see some differences there, but similar type of Claisen product, Dieckmann condensation product from a ketone using that. And I think you can look at some of these other ones here to see that. I'd like to go back to a problem we had in chapter 23 when we looked at making this. We were looking at sodium phenobarbital, which had this structure. Now, that drug requires us to use what? This malonate. And this malonate has the phenyl group right there, the benzene directly attached. So we can't do the malonic ester synthesis and have a phenyl leaving group there, okay? This is sp2 hybridized. So how are we going to do this? Well, if we get this product here with a phenyl group on there, oops, I got methyl. Sorry, I don't want to mix up my esters. Then we can do this, sodium methoxide and ethyl bromide. That reaction will work fine. But how do we get this? Okay, we can't alkylate right there from malonate, right? This is sp2 hybridized. So no alkylation there. What we can do instead is acylate right there. And actually, this is how it's made. So you can take this ester, methyl ester, with a phenyl already on there, and what? Treat with sodium methoxide and what? One of our carbonates. You can use dimethyl carbonate. Okay, and so you'll form the enolate here and tetrahedral intermediate, have it come down, kick off methoxide, and look, you put the other ester on there. And that's how they get around that problem. And so how would we make this? You actually make it from the alcohol. You have to oxidize, form the methyl ester. So that's chapter 22 chemistry, right, from previous section. How do we get that? Well, that comes from the phenyl Grignard. And I think you know what you need to add there, right? The epoxide, yeah. So anyway, these other acylating agents can be useful and can be used for other applications there. All right, how about intramolecular mixed Claisens? Yes. So we'll just do one or two of these and then we'll wrap up, okay? Remember, next time on Friday, no, we don't have class on Friday. So I'll be on the 27th. Actually, next Monday, we'll actually go back and finish 24. So we still got some more to do on 24. The last thing here today, I just want to show you one of these intramolecular Claisen condensations, where we've got, again, some choices to make here. So here's a gamma keto methyl ester. And we're going to treat this with sodium methoxide. So our standard conditions here in methanol, okay? And then dilute acid. So there's our Claisen conditions. Here's our Claisen, electrophile or nucleophile. But this is more of an aldol-like electrophile or nucleophile there. Let me give you the product here, and then I think we can figure it out. It'll give this product. This diketo cyclopentane structure. Okay, so let's analyze this. Where's our nucleophile? Where's our electrophile here? And what combination is going to give us what? This 5-membered ring, this intramolecular reaction. So let's see. Where can we form nucleophiles? We can form the nucleophile right here. Okay, because that's a alpha to the ketone there. We can also form the nucleophile right there, right? Because if we deprotonate there, then we got resonance there. Where else can we form it? Right here. Wow. So we've got 3 choices for our nucleophile. Which one do you think looks best? Well, we need to analyze where our electrophile is, right? Here's our electrophilic part right here, the carbonyl. Here's our electrophile right here. What combination looks best? There's only one combination that will give a ring size that's strain-free, or 5-membered ring. Let's see, if we have our nucleophile here and add to our electrophile there, what size ring is that going to be? Yeah, that'd be a 3-membered ring. We can draw that pathway and draw that mechanism, but none of that product is formed here, okay? That's our major product, over 80% yield. There's some other trace products that are formed here, but how do we form this major 5-membered ring? So not that pathway. Let's see, if we have our nucleophile here and our electrophile there, that's again a 3-membered ring. So yeah, we're already eliminating some pathways here that make sense, I think. How about this nucleophile here? Well, that would be redundant if that's the electrophile. That's actually just the resonance structure for the enolate formation. A 2-membered ring, right? No. Yeah, well, an alkene is really a 2-membered ring, right? If we have the nucleophile here and then attack there, what ring size is that? 1, 2, 3, 4, 5. Yeah. Okay, so there's our combination. So what will that look like? It'll look like this, where we'll have O minus and O methyl. Okay, now I went kind of fast there, didn't I? So I combine the deprotonation here. And you can do that with methoxide and form that first. And then go ahead and push those electrons into that carbonyl, okay? And that should give you that, okay? So go back in your notes and make sure that's clear. And then what? tetrahedral intermediate breaks down. We know that from before the Claisen. And we get here. Oh, there's our product. We're done, right? No, we're not done. We're under basic conditions, the Claisen conditions, methoxide, ethoxide. What's that going to do? Well, we've got that second hydrogen there, and that really helps us out. That's the only way these work, right? And here's our OME formed right there from the tetrahedral intermediate breakdown. So you can see why the deprotonation is very fast at that point. And so, yeah, there's going to be our new enolate. It's going to form right there. And yeah, it's resonance stabilized. You can draw a resonance structure with the negative charge here, and then keep pushing the electrons all the way up here too, right? And the pK of that, again, is around 10, okay? And that's really going to help you out because the pK of the original thing is around 20. That's forming reversibly into these conditions. So what do we need to do with the dilute acid? Well, there it is. Yeah, we need to have our acid here, and we can bring our electrons back down and then protonate there. So yeah, we finished off with a complex problem, I think. We've got numerous spots where it can be electrophilic and where the nucleophile can form. We'll pick it up there on let's see, where, yeah, on Monday. Yeah, remember, no class on Friday. So you got a few days here to catch up on your studying, and I'll catch up on my notes too and make sure we're in the right spot to wrap up chapter 24. We don't have much more to do. We've got a couple things. We've got a couple more intramolecular ones. We've got the conjugate additions and then the Robinson annulation. Remember, I said that's one of the trickier mechanisms. So read ahead, stay ahead of me now. It's a good spot to have this break. If you can take some time and work on the conjugate addition and the Robinson, and that will help you out here to keep this straight. So very good. We will see you next time. Thank you.